San Diego is the jewel of Southern California. People from all over the world come here to enjoy the surf, the sun, the culture of Southern California. They come here to do business, they come here to live, and they come here to retire in a virtual paradise.
Hi, I'm Dr. Pat Abbott. I'm a geology professor at San Diego State University. This allows me the great good fortune to live and work right here in San Diego. When we begin to think about why people are so attracted to this place, we have to ask ourselves, what makes it so desirable?
Well, we have a world-class zoo, we have a deep water bay that welcomes ships of the world, and we have a cultural and ethnic blend that puts energy, business, and life into the community. But thousands of years ago, long before San Diego ever had a name, people still came to this place. They came because it offered an abundance of food, both from the sea and from the land. It had a moderate climate, it was a good place to live, and with any luck, a place to grow old in relative comfort. But at the core of San Diego's success lies the actual shape of the land. And as geologists, we have peeled back the layers to discover the forces that shaped a land with so many attributes. It's exciting to look around a rich geological terrain like San Diego and know how it came to be. How did Mount Soledad form? Where did Mission Bay come from? Or Point Loma? Or the Silver Strand? Well, we're going back in time and speed up the geological time frame and watch what happens. Before there was a Mission Beach, before the cliffs at Torrey Pines, before Mount Soledad, before there was even a bay. We're going back to when San Diego was just a beach. The landscape of San Diego has been shaped by large-scale processes: rise and fall of sea level, regional tilting of the land, the shifting and warping caused by movements on faults in the Rose Canyon system. But changes in the landscape are barely perceptible when viewed during any given year. But if we apply a geologic measurement of, say, 1,000,000 years, then the changes become readily apparent, and this is the backbone of geology. That small changes, day by day, year by year, when viewed over millions of years, add up to major geologic effects. We can understand the shape of the land in San Diego during the last 1,000,000 years if we divide it into 3 acts. The first act opens with high sea levels retreating westward from a rising landmass. In Act 2, the Rose Canyon Fault alters the land. It changes the outline of the coastline. It raises hills, it lowers land, which fills with water to create bays. And in Act 3, from 14,000 to 9,000 years ago, as glaciers in the northern hemisphere rapidly retreated, the sea level rose, setting the stage to form some of San Diego's most remarkable terrain. I'm on the top of Mount Soledad. To the west lies La Jolla and the Pacific Ocean. On the south is Mission Bay and Point Loma. And at the base of the mountain, there is Interstate 5, where it connects with Highway 52. But when I sweep my eyes from northeast to southeast, I see a broad plain, cut through by valleys running from east to west. That's the Linda Vista Mesa. In the middle of the mesa is the Miramar Marine Air Station, surrounded by thousands of homes, businesses, roads, everything that a human being might need to survive in today's world. But 1,000,000 years ago, it was all underwater. If you know what to look for, you can actually see what we geologists call the 1,000,000-year-old sea cliffs. They're right here. And if you want to know what they look like in their prime, go just off today's shoreline and look back at the sea cliffs at Torrey Pine State Beach. Towering cliffs up to 300 feet tall with the surf pounding at their base. But behind the scenes, enormous forces were at work because the million-year sea cliffs are more than 9 miles from the ocean today. How did that happen? How did the sea cliffs and the ocean get that far apart? Well, several things began to happen at the same time. And remember, we're talking in geologic time. The seafloor began to rise, to uplift. And as the land began to rise in the east, the sea, simultaneously, began to retreat in a westward direction. As each bit of seafloor, in its turn, became beach, the ocean began to scrub and abrade the seafloor, creating a hard platform covered with sand and gravel several feet thick. This was later cemented together by salts crystallized from groundwater. The result is that today we have nearly flat ground that makes an excellent natural foundation for building homes, schools, and businesses. The uplifted and drained seafloors are dominant features in San Diego, but what happens when land is raised and exposed to the atmosphere? It meets the great equalizer, erosion. Bad for the land, good for us because it creates the valleys that provide habitats for plants and animals and opportunities for us. We're here in the Soil Erosion Research Laboratory. It's located in the Department of Civil Engineering here at San Diego State University. And the reason this apparatus was built is to learn ways to prevent erosion along California's roadways. And this is done by eroding different mixtures of earth materials to see how they erode on a much smaller scale. Here's how it works. Sediment mixtures are packed down, forming horizontal surfaces in this 12-foot by 30-foot bed. The entire apparatus is tilted, and artificial rain is applied with resultant erosion. In a small scale and in a short time, it gives clues to how a real area will erode. Just as these experiments simulate the erosion on a larger scale and longer time interval of given soil mixtures, it also demonstrates how the uplifted Linda Vista Mesa, the ancient seafloor, has been eroded by rainfall that has run off and carved the topography that we know today. We don't see it very readily because the sheer scale of the erosion is so great, it has actually turned gullies into valleys. As we drive uphill and downslope traveling about town, it is easy to get overwhelmed by the scale of the landscape. We lose perspective of the relatively simple origin of the mesa and valley topography. But the uplift and erosion are not the only forces at work here. As we near the modern coastline, we notice something else has happened. The landscape has been shifted, warped, and dropped. For instance, if you look at San Clemente Canyon, that's the canyon that houses Highway 52, you'll notice that as it runs west toward the ocean, it abruptly makes a 90-degree turn to the south-southeast. It then travels down Rose Canyon into Mission Bay. The land has been so distorted by active faulting that the very rivers that cut these canyons were forced to change their courses. They created new canyons across the regional slope of the land. They had to change direction because they met up with the Rose Canyon Fault. Now, in southernmost California, we have many active faults. The San Andreas, San Jacinto, Elsinore, Rose Canyon, Coronado Islands, the San Clemente Island Fault. And each of these faults has one thing in common. Their western side moves to the northwest faster than its eastern side. It's like two great ships on a collision course. They're both moving, but Western California and Baja California move faster and scrape by North America. They are traveling northwest on the Pacific Plate. All of these moving faults have major effects on Southern California land. but the one that most affects the topography of San Diego is the Rose Canyon Fault System. It begins along the east side of San Diego Bay and travels north through La Jolla, then runs offshore for 65 miles until the curving coastline causes it to come back on shore, where it is then known as the Newport-Inglewood Fault. And that end of the fault, the northern end, in 1933 caused a 6.3 magnitude earthquake that still reigns today as the second deadliest earthquake in California history. We know it as the Long Beach earthquake. It killed 120 people and caused damages exceeding 600 million in today's dollars. On the plus side, it was also the earthquake that was responsible for changing construction standards for schools and brick buildings in the state of California. Fortunately for us, our end of the fault has not generated a large earthquake, at least not in historic time. But in geologic time, the Rose Canyon Fault has been responsible for shaping much of the San Diego terrain, and it has done this in several ways. One way is called offset. Here we have layered construction materials representing the Earth. When I begin to turn the crank on this vise, the west side pushes out to the north. If this west side is viewed as a coastline, then the land, the shoreline, moves out into the ocean.
Visualize the faults tearing miles deep into the Earth. Does it tear on a single fault? Does it tear only on a single line? Let's follow the trend of the Rose Canyon faults on this photo.
Straight along San Diego Bay, straight through Old Town, straight along Mission Bay, straight up Rose Canyon. But just before reaching Highway 52 and Ardith Road, the faults bend sharply to the left. What effect does this left bend have on the land? These sheets of paper represent rock layers. If we push them to the north, like the Rose Canyon Fault moves, the paper deforms upward, like the rock layers do, to form Mount Soledad. If we keep pushing them, the rock layers deform downward, like Mission Bay, down below sea level. The hills and bays that help make coastal San Diego such a special place are due to the effects of the active Rose Canyon Fault system. Compression on the west side of the Rose Canyon Fault at the bend south of Ardith Road has warped up Mount Soledad, down-warped Mission Bay, and up-warped Point Loma. Pull apart in the zone between the ends of the Rose Canyon and Descanso faults has down-dropped San Diego Bay, which severed from the land to the east along the La Nacion fault system. Cross faults in the transfer zone lifted up the land to make both North and Coronado Islands. So we look backwards and study what has happened. And as we begin to see a clearer picture of the processes that created Mount Soledad or San Diego Bay or Coronado, then we can also begin to appreciate the numbers and sizes of earthquakes that accompanied these deformations of the Earth.